Right, so this is the CHEM5 June 2014 paper. We're going to go through it as I've done with other ones, start to finish, sort of fairly sort of quick, fairly non-stop. Aim being just to give you sort of a general idea of how to answer the questions, a little bit of theory, but concentrating mostly, as I say, on like exam technique and what to put down in certain questions. Hour and 45-minute paper. I'm hoping to do it a little bit quicker, maybe about an hour and a quarter, something like that. This is quite a good one. Unit 5 is a really good paper to score a lot of marks on. Normally in the conversion of marks to UMS, you're looking at this being worth 120 UMS. You can normally drop, in the past ones, you can normally drop about 20 marks-ish, 15-20 marks, and still score 4 UMS. So obviously people generally find it's a harder paper, but let's have a little crack on and see what's going on. Section A. Okay, write an equation of the process that has an enthalpy change equal to the electron affinity of chlorine. So, electron affinity, opposite of ionisation energy, we're essentially adding electrons. It's just a really weirdly worded question. Well, anyway, so we started our chlorine as a gas, as with ionisation energy, rather than taking away electrons, as we do when we ionise something in the ionisation energies, we're adding an electron this time. So add, oh that's terrible, add an electron, the result being the chloride ion, also gaseous. So that's a fairly straightforward. In terms of electrostatic force, suggests why the electron affinity of fluorine has a negative value. So the idea of it being negative, obviously implies sort of that it's an exothermic energy is released in that process. The energy is therefore not required to be put in. So first of all, I would say you're probably going to want to talk about that. Let's start with why. So what we will get is initially, when we're putting it in and when we're adding our electron, we're going to find that it's quite happy being added due to the fact that we have an attraction. So in terms of electrostatic force, it's just why. Okay, so there is an attraction between nucleus and the electron. The reason it's negative is ultimately that the product form is more stable. So the product formed is more stable. Therefore, energy released. 2 lovely little marks. Okay, so complete the Born-Haber cycle for silver fluoride by adding in the missing species on the dotted lines. Now this is actually one that I need to go back and actually tweak a video that I did on Born-Haber. You need to include electrons. That was my bad for not having included those, but it just needs to be there really. So I would always start, as I would if I was making this myself, I'd start this bottom half here. Silver, add fluorine in this case because we're making silver fluoride. So fluorine's F2, but because we've got an F there, it's got to be half F2. These arrows are literally signifying, so this arrow here is signifying the reaction, excluding the state symbols. It's actually signifying that reaction there. So that's what all of these arrows actually are, they're the reaction lines. So just get rid of that. Well, there we go. So we've got silver solid, add half of a fluorine molecule, oh, and we should also put obviously state symbols there as well. Fluorine as a gas, very important. You have the correct symbols in there. Okay, going up here, we're atomizing our silver, turning it from a solid to a gas, still keeping half F2. Going up here, we are then turning it into a positive silver ion, and it's this point here we've got to make sure we've got to include electrons, because we're making that positive by ultimately taking away electrons, so we end up with an electron free and the fluorine, sorry, gasify that one there. So there's our silver there. Top line here, what we're doing, well, this is remaining the same, we're still keeping this the same, but we can see from this point here we're then going to electron affinityize the fluoride, so, or the fluorine, but it obviously has to be as a single atom first. So we've got to atomize our fluorine. So we go up here, electrons, and then we are just going to have F as our gas, which then is going to work down, adding, taking away the electron from the fluorine, the whole thing being balanced up there. Nice. And that's worth, how many marks is that worth? 3 marks, so it's not too bad. But the important thing is include the electrons, and that's my bad in the previous video. I will make a change to that at some point, include those electrons. And besides that, that should all be reasonably fine. So going down, use the cycling question 1 to C1 and the data in table 1 to calculate a value in kilojoules per mole for the bond enthalpy of the fluorine-fluorine bond. So, bond enthalpy of the fluorine-fluorine bond. So what data are we given? Atomization, ionization. So we're given the atomization, ionization, electron affinity. Yeah. Minus. I don't know why I've just done that. And 955. Yeah. Okay. Now I am actually going to put all this. So it's this one. This is the one we're looking for right there. So I want to put all this data in. Atomization is 289. So process going from there to there, 289. Process of ionizing is plus 732. Now this is going to be a negative change over there. What's it going to be? Negative 348. So we're trying to calculate this change here, and that's the change of going from here, start, to here, finish. But we can't go from there to there, so we go around the houses on this one. So we're going to go against here, going to go against this, with this, with this, against this, boom. So let's start here. So we're starting there. So we're going against this one, against the arrow. So we're going to reverse the sign. So it's going to be minus 732 added 2. Against this one, minus 289. We're going with this one, so it's just minus 203. Or you could say add minus 203, it's whatever. Add minus 955 because we're going with that one. We're going against here, so we're going to reverse that. So it's going to be add in 348. And that's going to come to a total of 79 kilojoules per mole for that change. Where are we at? Here, going from there to there. But notice in this change here, what we're doing, and I'll go down here and explain this. The change that's actually within the Born-Haber cycle is half F2 to F. That's not the change that we want. We actually want the change of F2 to 2F. We want to break that F bond. Okay, that is the one we're looking to break right there. So we need to have the full F molecule to 2F. So this change here was 79 kilojoules per mole. So we've got to multiply that by 2 to give us 158 kilojoules per mole. Be careful of little tricks like that. They do like to put things in. I mean, it's only worth 2 marks. That's not a huge scoring question at all. Be very careful though. I mean, you'll get a mark for this, I believe, and then I think the second mark is going to be coming for the doubling. So you should still get the 1 mark fairly easily. This is the little trick right here. Just a little bit sneaky of them. There we go. 1D. So a theoretical value for enthalpy of lattice dissociation can be calculated using a perfect ionic model. The theoretical enthalpy of lattice dissociation with silver fluoride was plus 870 kilojoules per mole. Explain why the theoretical enthalpy dissociation of silver fluoride is different from the experimental value that has been calculated using a Born-Haber cycle. So the value we're given is plus 955 from the Born-Haber. Theoretical was plus 870. So we've got some differences there. So let's read the question once more. Explain why the theoretical enthalpy lattice dissociation for silver fluoride is different from the experimental value that can be calculated using a Born-Haber cycle. Okay, so basically what we've got here, if these values are similar, then it tells us that the theory is based on the perfect ionic model, which is this idea of point charges and all the rest of it. If our Born-Haber cycle value, the experimental value, is different, it actually tells us that we have a degree of covalent character, and that's a sort of nice sort of way of wording it. A degree of covalent character is being shown by here. Reason for that is that the theoretical model assumes point charges, perfect spheres, etc. Okay. Other way to say that is we've got degree of covalent character, and silver fluoride is not perfectly ionic. But I think I would probably go with this one here. Degree of covalent character. So explain why. Because there is a degree of covalent character, and it's different because the theoretical value assumes point charges, perfect spheres, etc. But obviously it's not, and that's the point. It is not perfectly ionic. It does not have these perfect spheres or point charges, and therefore is a difference to 2 marks there. Going down 1D part 2, the theoretical enthalpy of lattice association for silver chloride is 770 kilojoules per mole. Explain when this value is less than the value for silver fluoride. So silver fluoride, just write these values down so I can keep them there. That was plus 870. Silver chloride was plus 770. Now our lattice association is the energy when we're breaking apart this guy here. So it's going to be, say, AgCl to Ag plus and Cl minus if we're dealing with the second one here. So if our value is bigger, it would imply that more energy is therefore required to break this apart. So if it's a smaller value, as is for the silver chloride, then that to me says that so I'm going to say, so what's going on first of all. So explanation, attraction between ions, and that's the silver ions and the chloride ions, is weaker. Well, why is that? Well, the silver ion is remaining the same. That's the key thing. The silver ion's the same here. There's no difference there. Same charge. Fluoride and chloride ions, you know, both singly charged. So the only difference really is the fluoride versus the chloride. And one key thing is because chloride ion is larger. So the chloride ion is larger. Therefore, there will be ultimately a weaker attraction between the silver ion and the chloride ion. And there's your answer. That's 2 marks done. So that's a 12-mark question there. 1D. Quite difficult, I think, start to a paper. And Chem5 is not as nice as Chem4 in that respect. It kind of starts, I think, a little bit intense and just sort of keeps going on, actually. So, question 2. So we're going enthalpy change and entropies we're going to be looking at on this one. So on some more sort of thermodynamic stuff. So define the term enthalpy of hydration of an ion. Quite a nice one. So enthalpy change when 1 mole of a gaseous ion forms 1 mole of aqueous ions. Lovely. And that's this change here that we're looking at, I believe. Yeah, that's this change here, hydrationifying. Use data from table 2 to calculate a value for the enthalpy of hydration of the chloride ion. Right, okay, so we're going to have to think here, we're going to have to cycle this one up. So where are we at? Let's have a look. So let's okay, so yeah, should work. Okay, so silver chloride. So I'm going to do this as a cycle. I find it easier to do it this way, really. It's not the best drawing cycle, I'm not going to lie. Can I move those? Can I move that on this? I have no idea, in all honesty. Select annotations with a lasso. Oh, look at that. Yes, I can. I did not know that would work. So, I've got my silver chloride becoming the ions, and I've got the silver chloride becoming the aqueous ions, and I've just taken that from the table. So that's the first one, and that's the second one. Now, I can ignore this, because actually, for this one right here, probably have to undo that pretty soon, but for this one right here, I'm not dealing with silver fluoride, so I can ignore it. But I do need this one, the silver ions becoming aqueous silver ions, because that's this change here, the gaseous silver ions becoming aqueous silver ions. But this is the one I do not know. So if we say, we start here, and we finish here, and this is why I always encourage use cycles, because they're great actually. Same thing, Hess's law, no big deal. So we've got our values. I'll put the values in first. So minus 464. The aqueous one is plus 77. And what's that one? Plus 905. Big. So they're my changes. Now, going from here to here is the equivalent of going from here around to here. So what I can say is that, bear in mind, I've got to take into account both arrows here, because I'm going down here. I'm saying the equivalent of down here is the same as going round there. So question mark plus minus 464 is equal to, this is the tricky thing here, it's a bit sort of algebra almost, going against that one, so against that one, but obviously with this one. So minus 905 add 77. Rearrange that. My unknown is going to be equal to minus 905 add 77 add 464, and that should give me a value of minus 905 add 77 add 464. Bam. Minus 364. It's a dream. Kilojoules per mole. Again, not too much work there. You've just got to figure out what's actually going on. 2 marks, nice. Suggest why hydration of the chloride ion is an exothermic process. So why is the hydration of the chloride ion an exothermic process? Okay, so what's actually happening here? So chloride ion hydration, let's have a think. Okay, what we're going to find here, and this is, I think, quite a tricky one. It's a suggest one. Love a good suggest one. Think about what's actually going on. Let's think about the chloride ions. So we've got chloride. Think about the water. Now you should know we've got quite an electronegative little guy here. There, not so much. So actually, what we're going to find is that between these two, we're going to have an attraction. So there's going to be. Oh, I'm going to sneeze. Sorry, really terrible. Apologise. So, attraction between Cl minus and hydrogen in H2O, and the reason behind that is because H2O is polar, which is partly why sort of water, I guess, is quite good at dissolving things with that sort of polar nature of it. So there you go. Right, just so I'm happy with that. It's just, yeah, it's not the greatest. It's sort of horrible, really, but there we go. Going down 2 marks. Silver fluoride is insoluble in water at room temperature. Use data from table 2 to calculate the temperature at which the dissolving of silver chloride in water becomes feasible. Right, calculation of temperature. Right, so feasibility, we're talking about Gibbs, so we're doing delta G is delta H minus T delta S. Let's go. This is basically, let's go up and get some values actually. So I want I forget what the question was now. So temperature which the dissolving silver chloride in water becomes feasible. So it's this top, this is the one we're looking at here. So it's that one. So it's plus 77 is my enthalpy change, my, what's it called? Entropy change, plus 33. Now, the point where it becomes feasible, we can assume delta G is 0. So 0 plus 77 minus T times 33. With a bit of a rearrange, we can get to T is, let's have a look, yeah, plus 77. Just check, I'm going to add that across there. I'm going to divide it by 33, but what we've also got to remember, I almost messed that up there. Bear in mind, this is kilojoules and this is joules. So I need to convert my 77, my 77,000 there, or 77, sorry, into joules. So I'm converting my kilojoules into joules and multiplying it by 1,000. I'm just going to get rid of that plus, it's a bit messy. My temperature value there, when I work it out, is going to be 2,333 Kelvin. Remember, you've got to include your Kelvin. Do not put degrees Celsius. It's an absolute stinker. Comment on the significance of this temperature value. So we're looking at the temperature at which silver chloride will dissolve in water. Now 2,333 degrees Kelvin is a little high, and it's actually higher than boiling point of water. So actually it's really not going to work. It's going to be a little bit of a stupid one to do. So it's higher than the boiling point of the water. So another kind of almost comment, suggest again, similar thing, using your brain a little bit. When silver fluoride dissolves in water at 25 degrees Celsius, the free energy change is -9 kilojoules per mole. Use this information, the data from table 2, to calculate a value with units for the entropy change when silver fluoride dissolves in water at 25 degrees Celsius. So again, we're going to use delta G is delta H minus T delta S. We're told the free energy change is -9. Where are we going now? Let's have a look. What am I doing? Silver fluoride this is now, yeah. So enthalpy change is -15, and I'm going to calculate the other one. So I know my enthalpy change is -15, 25 degrees Celsius, which you should know is 298 multiplied by delta S. So it's going to be -9 add -15. No, it's not. It's going to be -9 add 15. Divided by 298. But again, this needs to be a times by 1,000 actually. About value there. Just realised actually, I probably explained this quite badly. Back up on here where I did the 77 divided by 1,000, in theory is actually just a little bit easier. It's the 33 we're actually converting. So go back up to the top here. Because we're dealing with kilojoules here and joules here, we need to convert this in theory to the kilojoule. So you're dividing this by 1,000. But when you're doing the maths here, it's a little bit easier often to do because you can probably do that in your head. 77,000 is just the same as having divided by 33 divided by 1,000. So if mathematically it's the same. So maybe a bit confusing there. So I apologise if that's tripped you up at all. I'll do it the right way here, and I'll undo what I've done there and just work through. So I'm actually going to leave that as it is at this point, and that's going to give us our delta S. It's a bit of working out on that one. -9 add 15 divided by 298, 0.02. Bear in mind that's 0.02 kilojoules per mole, because obviously doing all our values here in kilojoules. If you want to convert it to joules per mole, it doesn't specify units, you don't necessarily need to. You're obviously going to times this by 1,000, 20 joules per Kelvin per mole. Yeah, so normal delta G, delta H and all the rest of it. Rearrange your equation. I've not done any factors of multiplying and all the rest of it. I've done left up to the end because it's obviously delta S where we get our different units with our joules normally. Kilojoules per mole here, kilojoules per mole is fine. Stick the numbers in, divide them by the temperature to give you our delta S, which is in kilojoules there per Kelvin per mole, or basically convert it to joules there, and that should be kind of reasonably straightforward. Going down then to question 3. This question is about some period 3 elements and their oxides. Question: to decide what you observe when in the absence of air, magnesium is heated strongly with water vapour at temperatures above 373 Kelvin. Write an equation for the process, the reaction that occurs. So, magnesium is heated strongly with water vapour. We would find bright white light. We would see white powder or residue remaining. The reaction with this one would be Mg H2O H2. So nice, is it? Note that because it's strong water vapour, you don't produce the hydroxide, you just produce the oxide. It's a bit of a strange one in that sense. That reacts almost like this sort of as it would do with oxygen almost in some ways. Explain why magnesium has a higher melting point than sodium. Metallic bonding here. Mg2 plus has a higher charge, so it's almost unit 1. Therefore, stronger attraction between metal ions and delocalized electrons. 2 marks. It's quite a nice one. That's very, very AS, really. 3C. So the structure of and bonding in silicon dioxide. So again, we've got this idea of really AS, which obviously repeats itself in the periodicity stuff, which this question is about. Structure here, giant covalent. I'd probably go for macromolecular. I'll go giant covalent, but macromolecular, giant molecule, one of the two though. Bonding is therefore covalent. So quite an easy question, that one. 2 marks there. Physical property 1, I would go, other than high melting point, or nearly went that one there. Hard, doesn't conduct electricity. 4 marks. That's probably the easiest 4-mark question you're going to come across on a CHEM5 paper. Get the formula of a species in a sample of solid phosphorus 5 oxide. State the structure of and describe fully the bonding in this oxide. So, formula first of all. Get the formula of a species. Sample of phosphorus 5 oxide. So we're going to have P4O10. Structure, it's a molecular or simple molecular. I sometimes would say simple molecular, but it's that idea of covalent really then again. So covalent. But remember, in between the molecules, we have weak van der Waals. And you've got to make sure it's between molecules, which back in sort of, GCSE you would say is weak intermolecular forces. So covalent bonding within, I should say, within molecule. Weak van der Waals between the molecules. 4 more marks there, quite nice. Sulfur 4 oxide reacts with water to form a solution containing ions. So sulfur 4 oxide, SO2, reacts with water, H2O. Oh god, what's on here? So what we're getting is we're forming that acidic solution. So go H plus H SO3 minus. So it's that sort of the production of sort of the sulfurous sort of acid we're going there. Write an equation of the reaction between the acidic oxide, phosphorus 5 oxide, and the basic oxide, magnesium oxide. So magnesium oxide, MgO. Phosphorus 5 oxide, I already had that question, P4O10. And we're going to produce that H3PO4H. Yeah, so we're going to produce the salt in that case. In this one it's going to be, oh, let's have a think what we're going to do. 3 minus 2 plus 3, 2. This is going to need balancing up, so I think we're going to go for, would 3 there work? Too easy. No, we've got to double this actually. Make the phosphorus is equal. So that's phosphorus equal, which means we'll have a 6 there, and that should balance up a treat. So it's a much easier question. 15 marks though, I think much easier than question 1 and 2 actually. Maybe a bit of sort of repetition, sort of just recall. Question 1 and 2 quite heavy I think on the maths and stuff as well. Fine, a nice little bit of a transition metals. So consider the following reaction scheme that starts from aqueous copper, the hexaqual copper 2 plus ions. So starting here we've got reactions 1, 2, 3 and 4. So reaction 1, going from there to there, pale blue, precipitate. We want to think of a reagent. We need the copper containing species. Because it's the precipitate, we're looking for that non-charged form of the copper. So reagent, couple of choices. We'll go ammonia, but it could be sodium hydroxide, not OH minus. Don't trip up on that one, that's not a reagent. The copper containing species is going to be copper 2 plus. It's going to be CuH2O4 OH2, and then equation. So CuH2O6 2 plus. I'll do it with NH3. CuH2O4 OH2, add 2 NH4 plus, and what we've done, obviously we've removed 2 hydrogens from the 6 waters, therefore leaving us the 4 waters and the 2 hydroxides there, and we're going to need a 2 there as well, which balances it up treat, I believe. Yeah, 2 plus 2 plus, yeah, nice. Okay, reaction 2. What's reaction 2? So the powdered blue precipitate turns into a deep blue solution. So the reagent, ammonia, we'll stick with on that one. So we're going to go ammonia, and it is going to be, in this case, it's the amine version, the ammonia, when the ammonia actually comes in and gets some substitution going on. So this one's copper containing species, miles away there, H2O 2 NH3 4, still 2 plus there. The equations, so we're starting with the CuH2O 4 OH2. We're going to react that with ammonia, and ultimately going to end up with this guy here. So we're going to go CuH2O 2 NH3 4 2 plus, and then what's obviously remaining, 2H2O 2 OH. minus. I need to balance this up there for ammonius. Because obviously copper being sort of a bit funny on that one that goes on there. So reaction 3 this time. So we're going from the hexa aqua down to the green blue precipitate. Again, not charged there. So what's our reagent going to be? What we're looking for sodium carbonate this time. Copper containing species is going to be CuCO3. Reaction's quite a nice one. Start with our H2O 6 2 plus. Stick with the ions. That's the way to do this one. CuCO3 and 6 H2O. It's all balanced up nice. Yep. So we can see 9 marks so far on there. Loads. And then another 3 here, so 12 marks. Reaction 4, the final one, we're going from the copper 2 plus to a yellow-green solution. Right, so they're going the next way now, and we're going to form, well, we're going to react it with HCl. What we're forming is copper, not copper chloride, but the tetrachloride there, which is going to be 2 minus. Starting again, CH2O 6 2 plus. 4, just that balance one as we go. CuCl4, that should be 2 plus there. No, it should not be 2 plus at all. Ignore that, then why I've just made that change, it's ridiculous. 2 minus, sorry, because obviously we've got the 4 chlorides there, and 6 H2O for our equation. Oh, it's loads of sort of memory stuff there. Working, just basically, you're not going to be able to work like that out. You've just got to know it, which is a bit grim, but you've just got to get through and learn sort of that. Question 5 shows some standard electrode potential data. So here we go. Give the conventional representation of the cell that is used to measure the standard electrode potential of iron, as is shown in table 3. Okay, so we've got iron there. Right, so we're going to have use our hydrogen electrode, salt bridge, and that guy there. So is that right? Yeah, that's right. Yeah, that's fine. Miles away there. Reference to electrons give the meaning of the term reducing agent. So reducing agent is an electron donor. 5C. Identify the weakest reducing agent of the species in table 3 and explain how you deduce your answer. So because it's the weakest reducing agent, remember that reducing agents themselves are oxidized. So both those things, we're looking for the most positive number here. Straight away we've got one here. Okay, that is going to be the weakest reducing agent. It's going to be the most, it's going to be the best oxidizing agent. It's the most easily reduced, but it's not the best weakest reducing agent, so it's going to be that one there. Now the key thing is here, you may be tempted just to stick down HOCl. Well, that's not correct, because actually this reaction here, HOCl to Cl2, here we've got -2 +1. This is actually +1 here, going to 0 there. So that's actually reduction. So this is not being oxidized. It's actually the chlorine going that way is being oxidized. So it's the chlorine is the weakest, has the highest potential, electrode potential. 2 marks there. Nice, nice, nice. Down a bit more. 5D. When HOCl acts as an oxidizing agent, one of the atoms in the molecule is reduced. Place a tick next to the atom that is reduced. So, which one of these is reduced? What was the question? Oh, I didn't see the Cl there. Good. So yeah, I've already mentioned that. So it's the chlorine that is reduced. It's going from that +1 and so to that 0 state there, which is good. Explain your answer to question 5D1 in terms of the change the oxidation state. Okay, that's exactly what I just said. So Cl goes from +1 to 0. I'd probably go +1 in HOCl to 0 in Cl2. Give it more there. 1 mark though. Nice. Using the information table 3, given table 3, deduce an equation for the redox reaction that would occur when hydroxide ions are added to HOCl. So let's have a look here. So there's our hydroxide ions added to HOCl. So this is the more negative, so we're going to have oxidation and we're going to have a reduction occurring, being the most positive. So which species is going to react with which? Oxidation there. So -2 and 0. Yeah. And this is going to be the reduction. We've already said that. Yep. So it's going to be that way round. So that way going to there. So almost made a mistake there. So obviously we've got to balance up here. We're going to multiply this one by 2, giving us the 4, 4, 4, etc., etc. In total, that's going to give us 4 HOCl, add 4 H plus, add 4 OH minus, go into 2 Cl2, add O2, add 6 H2O. Love a good equation, redox equation. There you go. That's the equation done there. Table 3 again. They are loving table 3. The half equations from table 3 that involve zinc and oxygen are simplified versions of those that occur in hearing-aid cells. That's good to know. So here's our cell. So use the data from table 3 to calculate the EMF of this cell. So we're going to have so this one, trying to work it out. So that's going to be right. So it's going to be 0.4 minus, but the other one was minus again, minus 2 minus blah, 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 and that's going to give us 1.65. 1 mark, nice. Use half equations from table 3 to construct an overall equation for the cell reaction. The cell reaction is going to be, as I said, I've already said it's this one and this one. Cell reaction, there's a lot of crossing out there actually. There's oxidation, so we're going to go zinc that first. Reduction's going to be, yes, this is going to be our oxidation, more negative. This is going to be where our reduction takes place. So we're going to start with zinc. We're going to go that way. We are going to have to cancel quite a lot of waters and all sorts. And actually, when you start looking at that and you actually cancel it all down, which you're working for here, I'm not going to do that. You end up with 2Zn plus O2, 2ZNO. So that's cancelling all those hydroxide ions and all the waters as well. Gives you that as a basic equation. Again, 1 mark. Not giving you a lot for that. Identify which of A or B in figure 1 is the positive electrode. Give a reason for your answer. So A or B, which is the positive electrode? Right, so we've got zinc powder there. Positive electrode is going to be where the reduction takes place. So it's going to be, yeah, it's going to be that one there. Air hole here. So that is where that's going to take place. The reduction is going to take place this bit here. So it's going to be A. Positive electrode is going to be A. The oxygen obviously coming from the air hole. And best way really to say that, the oxygen, let's back up at this, stainless steel lid, air hole, electrode there. I'd say I'd go oxygen is reduced, or the oxygen has more positive. Yeah, you don't need both of those either, but I'm not sure which one I'd choose. Probably go. I think that one I like better, but exam-wise, I think they're going to prefer that one. Right, so F4. Give one of the reasons other than cost why this type of cell is not recharged. I guess one answer, if you reverse these, we're actually going to go that way and we're going to produce gas, which obviously a gas build-up inside here is not really ideal. I'd go that one. The other way to think of it is it's probably quite unlikely that the zinc oxide is going to get turned back into zinc. But I quite like the idea of O2 produced, therefore danger of explosion. That to me seems like the most plausible answer. So that's question 5 done, 14 marks there. Let's hit question 6. A bit more. It's the batteries, fuel cells this time, the hydrogen oxygen fuel cell. Hydrogen oxygen fuel cells, the half equations. We are looking at. Apologies. I'd probably go for simplicity. What am I doing? Probably go for those ones. There are different ones. You can put OH minus in there as well if you wish, but quite like those two. Use these half equations to explain how an electric current can be generated. Well, this one produces electrons or releases electrons. So hydrogen electrode we'll say produces, I suppose it does produce them, doesn't it? And the oxygen electrodes accepts them. So we've got ultimately that flow of electrons, therefore, and that's our current there. 2 marks. Why a fuel cell does not need to be recharged. Yeah, this one. So why does it not need to be recharged? Constant supply of fuel, so hydrogen, basically constantly fed in, therefore 1 mark again, so we don't have to recharge it. To provide energy for a vehicle, hydrogen can be used to even fuel or internal combustion. It's just main advantage, hydrogen a fuel cell rather than an internal combustion engine. I'd go in that one, harnessing more energy. Internal combustion engine, you're not being able to use necessarily all of that energy. Some of the energy is going to be wasted, going to go to other places. Here we're going to get to use all that sort of energy that's there as from the current. We're going to use it obviously to power our motors and all the rest of it. So how can we word that? I'd probably say less energy is wasted in the fuel cell. Therefore, more energy released is used as useful energy, or whatever, converted into useful energy, whatever you want to say. But I think less energy is wasted sort of highlights the point there and gets us to where we need to be. 6D, one major hazard associated with the use of hydrogen oxygen fuel cell in a vehicle. Classic answer there from GCSE again. Hydrogen is flammable, and obviously if you're walking around with a big tank of hydrogen in your car to constantly feed that fuel cell, you crash, you're going to have problems. So hydrogen flammable, could also have explosive as well. One more mark, 7 marks there. So on to section B. I think there's only 8 questions on this one. So on to section B. So look, red, violet, green. Anyway, coloured ions, complex ions, and all the rest of it. Blah 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 blah. And we're talking about chromium here and the colours. But it's explained with reference to oxidation states and electron configurations why the chromium ions and complexes P and Q contain the same number of d electrons. You should not consider the electrons donated by the ligands. Explain in terms of electrons why they're different colours. Right, so first of all, okay, that's actually quite a nice one. In each complex, chromium, basically we've got the 3+. Chromium is Cr3+. Therefore, same electron configuration. And you could say the 3D electrons, but it's up to you. Why are they different colours? Well, different ligands. And then that's we need an explanation. That's really sort of not giving us the reasons behind it. So different ligands, therefore, how are we going to word this? Different d-electron energy, different split. Yeah, different energy split of d electrons. Therefore, different wavelengths or frequencies, you can say. Absorbed, and therefore different wavelengths emitted. Actually, quite a nice question, that one. Nice bit. You can really sort of get your teeth into this bit here, tie into that sort of reasons behind the colour, which is quite nice. And this first bit's actually quite straightforward compared to I think the rest of the paper, which has been in parts a bit tricky. That was not too bad. So that's 6 marks down. That was 7A. Lots of space as well. 7B, write an equation to show how the cobalt NH362+ reacts with 1,2-diaminoethane. Right, okay, so we know we're going to start with, let's first of all, what's 1,2-diaminoethane? So it's going to be NH 1, 2 diamino ethane, so it's going to be NH2 CH2 CH2 NH2. So we're going to have cobalt, hexaamine, 2+ we're dealing with. It's going to react with that NH2 CH2 CH2 NH2. Each of these nitrogens, remember, has got one of these. So we're going to 3 of those to substitute it out completely. We're going to end up with, oh god, CO, NH2, CH2, CH2, NH2, 3, 2+, add 6 NH3 on there, which I think is quite nice. Good, yeah. Thermodynamic reasons. Why does this reaction occur? Right, so 4 becomes 7. So I would say that 4 molecules become 7. Therefore, disorder increases. Therefore, entropy increases, obviously, again. Um, 5 marks. Disorder increases, entropy increases. Oh, okay, yeah. So, disorder increases. Right, yeah, enthalpy, excuse me, enthalpy change-wise, think about it. Cobalt, it's the nitrogens basically, with 6 nitrogens and 6 nitrogens, so enthalpy change approximately 0, because ultimately you've the bond's broken. You've got the same bonds, same type of bonds being broken and formed in both cases, so we haven't really got an enthalpy change there. And delta G is negative. There we go. So at the latter end there, I think a bit more difficult, but certainly 3 of those 5 marks, I think, sort of very achievable. Okay, the toxic complex cisplatin is an effective anti-cancer drug because it reacts with the DNA in cancer cells, preventing cell division. Draw the displayed formula cisplatin. Okay, so displayed formula. So we've got our PT in the middle. We've got our 4 bits there. The 2 chlorides, and then make sure we do the obviously have the NH3s on there. Okay, charge equals 0. Nice cancelling sort of effect there. One of the bond angles at platinum, bond angles 90 degrees, is that square planar shape. That's everything, yeah. When cisplatin is ingested in an initial reaction, it involves one of the chloride ligands being replaced by water. Okay, so add water. It's going to end up giving us but because we've obviously removed one of the chlorides, it's going to be positive overall. And a chloride there, nice. It's just how the risk associated with the use of this drug can be minimized. Again, suggest with any sort of drug, reduce the risk. If you need to use it, then you could use it in small amounts. And I'd probably stick with that. Or target the use. I'd go with using small amounts. Probably not going to help. Or yeah, target where you're going to use application. So using small amounts. 7D. Explain with the aid of equations how and why vanadium 5 oxide is used in the contact process. You can see you need to just know, you need to remember a lot of stuff from this. There's 2 equations you're really dealing with. V2O5, SO2, V2O4, SO3. First, second one is going to be reforming that V2O5. So stick our oxygen in and V2O5 there. So it's used as a catalyst. So this is how sort of it's used here. Why? Used as a catalyst, so speeds up the reaction. 4 fairly easy marks. Actually, if you can remember your equations, certainly those 2 marks there, very easy to get. There's 20 marks on question 7. So we're on question 8, and we're not a million miles away from now. What have we got? Oh, just those 2 there. Almost so close. Student carried out an experiment to find the mass. Good calculations. Find the mass of FeSO4 7H2O in an impure sample X. Student recorded the mass of X. The sample was dissolved in water and made it to 250 centimeters cubed. Oh god. Of solution. The student found that after an excess of acid had been added, 25%. Good. Nice ending question. So, right, okay. First of all, let's calculate our moles here. So the moles of the dichromate. That's our first bit of information. Concentration times volume, 0.0150 times 21.3 divided by 1,000. That's going to give us 3.195 times 10 to the minus 4. Now, this is a horrible question, actually, because there's loads to do for 5 marks. You just need to know the ratio of the equation. Oh, horrible people. So the reaction that's occurring is the CR207. CR207 to minus sorry. CR3 plus. When we balance that up, we're going to find. We're going to put here 7H2O, 14H plus, 14, 12, 6, nearly forgot that, 6 electrons. The iron is basically going from 2 plus, because it's the FeSO4, so it's the 2 plus, and it's going to 3 plus. We're going to multiply that by 6. Ultimately, what we're going to end up with, I'm going to skip a bit here, ratio of this to this is 1 to 6. Okay, the reaction. So we know therefore that moles of Fe2 plus are 3.195 times 10 to the minus 4 multiplied by 6. That's giving us 1.917 times 10 to the minus 3. Let's check, get my head around where we are now. So that's reacting with my Fe2 plus. That's my moles of Fe2 plus. Now that's in 25 centimeters cubed. So it's that times 10, so it's going to be 1.917 times 10 to the minus 2 in 250 centimeters cubed. Oh, we're doing then, yeah. So we've got our moles, we're just doing mass then of the FeSO4. We know the moles of it because the moles have all come from the Fa2 plus. We know what the moles of that thing must therefore be. 1.917 times 10 to the minus 2 times 277.9, which is our MR of said thingy compound, and that's going to give us 5.33 grams. Actually, it's not too bad. It's not too bad of a question. A bit tricky though, because you've got to stick that in the middle there again, and they don't give you a lot of detail about that. But 5 marks, not too bad. Last bit, the student found the calculated mass of FeSO4 7H2O was greater than the actual mass of the sample. Weigh it out. Okay, so we would need to. What would happen is what's present here, what's doing the reacting. One way to do it, what's doing the reacting, would need to ultimately react with more dichromate. So, for example, because dichromate, yeah, if the impurity reacts with the dichromate, it's going to use up more dichromate, which is therefore going to have that cascading effect. It's going to give us more moles at the bottom, which is therefore going to give us a larger number of moles of the FeSO4 7H2O, which is therefore going to throw the mass off. So yeah, so impurity reacts with dichromate, therefore, and then if you think about it, the impurity Must react with more. For a given mass. Yeah, that's the one. So it must actually react with more of that than the iron sulfate, the hydrated iron sulfate would do to actually create that sort of that dodgy result. Not a bit of a, that's a horrible, horrible, horrible last question, which again you'd expect because it's the end of the paper. Anyway, that is the CHEM5. That's the June 14 paper. Not an overly easy paper. The CHEM5 is a bit of a tricky one, but as always, I hope that has been of some help. Any questions, stick them in the comments. But there you go.